like to thank Alan and Brad and especially Scott Brandberg for the invitation to be here today. If I understand the assignment, it's to give a very dull technical lecture in the next 11 and a half minutes. So, what I'm going to share with you is our ideas that got put into what's like a pre-proposal for what we call the rate case. So this is the back and forth between our large electric utility and our regulatory agency. So what I'll be sharing with you is from an open public document, and if I hadn't mentioned it to you just now, I doubt that any of you would have gone to look for that. So I'm just going to try to pull out some thoughts that I hope can be generally useful to others. So through a long process of reading all of the available government reports on functional recovery, infrastructure resilience, there were some things that I felt needed to be tied together with some thoughts that I'll be expressing here in this presentation and that are in our RAMP application from 2022, Chapter 8 on Seismic. So that's what I'll be drawing from here today. If I could have the next slide, please. Maybe I'm supposed to do that. Okay. I'm going to present 3 thoughts or themes, the first of which is very simple, and that is intersections. So as some of my former students who are here all know from UCLA engineering geology class, what I was encouraging them to think in terms of is simply where 2 lines cross at a point. Imagine a fault line and a lifeline. At that intersection point, the risk is concentrated and is extremely high. So if we focus our attention to places like that, we can very cost-effectively buy down seismic risk. So that's idea number 1. Idea number 2 is, we call it our resiliency pyramid. It's a simple triangular diagram with our most critical facilities at the top, and at the base of the pyramid, a large number of critical assets that are just not as critical as the stuff at the top, but also can't be ignored because they're also important to providing electric power service to our customers. By the way, we have 5 million meters. We serve about 15 million people in the Southern California region. And then that third thought that I want to get to, but I'll probably have to just sketch it, is that the natural systems, the earthquake fault system, the earthquakes themselves, all follow power law distribution, essentially. And the infrastructure systems that we've built, the complexity there is such that we also have this large base of the pyramid, and a lot of the risk is really focused at the top of that resiliency pyramid, where we just have a small number of critical assets. So if you combine those 2 thoughts that I just mentioned, you realize that scaling is going to be challenging because we're looking at nonlinear systems, and both natural systems and human invented systems to provide power. The other thing we're doing here is combining our 2 primary drivers, one being safety and the other being reliability. So we try to take all of those things into account in our system design. And the main thing that I'm responsible for doing is figuring out how to prioritize projects to retrofit our existing infrastructure. And of course, the other whole side of things is we're also trying to innovate and build out the grid of the future. So there's also that challenge as to how to place critical facilities in the future and how to design them, and what are appropriate ground motions for design. Next slide, please. I better figure out how to do this here. There we go. So our service territory is the yellow line, and you can see it's diagonally cut by the San Andreas Fault in the red dashed line here. We don't only worry about the San Andreas, we do worry about it quite a bit. We think about it, and in terms of our earthquake preparedness, we devote a lot of effort to considering what we might experience in case of a big one on the San Andreas. But we also have a number of other faults labeled here, and then hundreds of other faults that aren't even labeled. And we don't know where the next big earthquake is going to occur. So we have to be ready for anything in our service territory. I just labeled the Ridgecrest sequence 6.4 and 7.1 from 2019 as examples of earthquakes as part of the San Andreas fault system writ large, but on one of those other secondary faults. So we really do need to be ready to respond no matter where an earthquake occurs in our service territory. A couple of other things here I want to mention. The hexagons, the white hexagons are indicating the port complex and downtown Los Angeles. So I mentioned about how where a lifeline and a fault line cross, you can get a risk concentration. But also through the development of our society and our infrastructure, we have risk concentrations apart from the faults, where in this case, at the port complex, some of the lifelines originate at the refineries, for example, connecting out to points to the northeast, goods movement, liquid fuel pipelines. And then the downtown Los Angeles area is, of course, a place where, because of all the tall buildings and all of the essential and critical government functions that are housed in buildings, some of which are older. By the way, there was just an LA Times article just the other day about 33 of the LA County buildings that are being assessed and may need seismic retrofits. So those are places where the risk is high, and we need to take those into account in our approach as well. So now back to that title of Intersections, a Strategy for Increasing Infrastructure Resilience. Here I take that red dashed line, the San Andreas Fault. You can see the probabilistic hazard overlain here. This is from a 3-year-old FEMA report working with USGS. The dark blues are 250 occurrences of damaging shaking in the next 10,000 years. So of course, that band of concentrated hazard along the San Andreas and its neighboring subparallel faults like the San Jacinto and Elsinore, you see that familiar pattern. But what I'm overlaying here along with the red dash line of the San Andreas is just a notional lifeline connecting from the port complex, this dashed yellow line. That might be, just for example, a transmission corridor, or it might be a fuel pipeline going from the, as I said, from the refineries out to Las Vegas, for example. So picture that. You're trying to move liquid fuels that have been refined out to Las Vegas. Well, you need to put those fluids under pressure in order to get them up through and across the San Andreas Fault at Cajon Pass. So you have buried steel welded pipelines that were installed decades ago that are moving pressurized liquid fluid, gas, diesel, and jet fuel, and so forth, right where the San Andreas crosses. So that's one of those risk concentration points right at Cajon Pass, where you also have co-located goods movement, 2 major rail lines, high-pressure gas lines, and our transmission corridors go through there, as well as LADWPs. So that's a sort of a well-known, well-recognized concentration point where in a future earthquake, if the San Andreas has surface rupture through there as well as strong shaking, we're expecting to see a lot of damage and a lot of concentrated impacts and a lot of interdependent co-located lifelines affecting one another. So that's that white circle representing where risk is extraordinarily high. So we focus in on those places where we know we can have the most impact by doing mitigation actions to improve the lifeline infrastructure resilience. Now, one of the parts of the assignment here in the Geo-PIT was to talk about successful case studies. This, I think, is the world's leading example to this day of when engineers and geologists in particular work together, they can really do amazing things. And this is the Trans-Alaska Pipeline, right where it crosses the Denali Fault. A condition of the permission to establish this pipeline was that they had to take into account the fault, and they had to design for it so that in case of a future big earthquake, no oil would be spilled. So the Alyeska Pipeline Company engaged a team to identify the location of the fault and design a modification to how the pipeline is normally over permafrost areas. It's above ground. And they adapted it so that it had railway metal with Teflon on top, and those could slide. The dog legs you see in the pipeline are also normal, part of the above permafrost design to allow for expansion, contraction, and flexibility. And so the idea here was that when the fault broke, the whole thing could slide, adapt, and adjust to the new configuration, and it actually worked in the 7.9 Denali earthquake in November 2002. So when the design is done right, for new infrastructure, we can have tremendous success like this case. Unfortunately, most of the time we're dealing with needing to figure out how to retrofit existing infrastructure. Very different situation. So I've mentioned Cajon Pass. The white circle here also represents Cajon Pass, just like in the previous diagram. Now overlain behind it is the expected shaking pattern from a future 7.8 San Andreas earthquake. This is called the shakeout scenario. There was a major report done by a team of over 300 scientists and engineers back in 2008 that many of you were a part of. So thank you for that. And at Cajon Pass, if you go there in the field, you see a little montage of photographs. You see placards for buried fiber optic trunk lines for all the main carriers of telecommunications. So that's your internet, your cell phone, all of it carried in fiber through there. You see those two rail lines I mentioned, the power lines and the buried fuel pipelines, all of that co-located. You know, and in a secondary but also very important example, the white oval down by Indio and going up toward Whitewater, that is an area where we also have concentrated lifeline infrastructure crossing the San Andreas Fault. So these are places where we know that when we use that approach of looking at the intersections, we can zero in on where we may have some existing infrastructure that may need another look, further assessments and then design engineering solutions to help ensure that in a future earthquake that we can withstand the hard hit of surface fault rupture, other kinds of ground failure, and shaking. This is just a sampling of photographs from past earthquakes showing you lifeline disruption. Laval Lund, who brought me into this field of looking at lifeline infrastructure resilience back after the '92 earthquake, you know, we were looking for those rare examples of where you could see severed lifelines and get photos of them from the field. So with the recent earthquakes that have impacted Turkey and Syria, we're seeing just flooding in many, many photos, as you saw this morning from the panel, of more newer examples of lifeline infrastructure disruption and damage. So we try to learn lessons from these examples. Now, I said that after talking about intersections, the next thing would be I wanted to explain the resiliency pyramid. Now, I think probably what you're thinking is, Ken, that is not a pyramid. You can't fool me. That is a triangle. And you're right. I tried to simplify it. As I said, up at the top, you've got your most critical assets. That's what we call tranche one. We didn't invent the name. Our regulators told us, we want you to innovate, design a approach that uses tranching of assets. So here, what we do is we do sort of full assessments on our tranche one assets, medium level on our tranche twos, and so on down the line. So if you just sum up our tranche one, tranche two, and tranche three, it's about 1,250 critical facilities. And then the base of the pyramid, we have over 21,000 lattice towers that are holding up the high voltage transmission lines. So we have a lot of residual risk. So the challenge is to prioritize projects and spend money efficiently. So with this tranched approach, one other thing I want to mention right now, I said I was going to have to sketch this and just mention it briefly, but the tippy top, that's 20 assets in tranche one. The next one down has 88, and then tranche three has 1,000. So you can see right away the sides of this triangle or pyramid shouldn't be represented linearly because it's really, really focused at the top. And that's where I was saying how this is nonlinear and we need to take that into account. Basically how that plays out is we just put even more focus on the assessments and mitigation and design for our most critical assets. So that's how we're implementing this. So an example of a facility from the tippy top of the triangle, this may be familiar to some of you who are owner-operators of infrastructure. You've got to have data centers, and these are like the nerve center or the brain, really, of the organization. So everybody running whatever software that is to do their email and everything else, it's all on servers and computer equipment racks in buildings. So we do structural and non-structural assessments to ensure that our real-time objective recovery times for our 8-hour and 24-hour essential and critical functions that are in our business impact analysis, all of that gets channeled towards our strategy for our assessments and our mitigation projects. So this is just a couple of example photos of a data center. But here you have a relatively easy job to do. You need to focus in on where you've got all those essential and critical applications housed in one building. Now, the tricky part of that is all the stakeholder engagement, because even in a single computer equipment rack, you might have 12 different departments with equipment in there, and so you've got to make sure that you're not interrupting anybody's essential and critical functions as you do the work. But at a single site, the hazard is relatively uniform, risk is concentrated, so that's a relatively easier problem to solve in some respects. Now we take a look down at the base of the pyramid. I mentioned we have over 21,000 lattice towers like the two pictured here. From the 1992 Landers earthquake, you see here on the right an example of a tower that had 2 feet on either side of the fault rupture on the primary surface rupture of that earthquake. And yet the tower remained functional. There was no disruption to service through that line. Similarly, in Turkey, we have an example. The yellow dash line is going through the surface rupture, and you see off in the distance the tower there has been also bisected. And so we know that we need to accept a lower risk spend efficiency when we're looking at long linear assets like these. So we can do it all. We can fold in and consider all of those types of assets in our approach. And this is just accomplishments to date. Edison has invested between 2016 and present over $150 million in prioritized targeted projects. So the challenge is partly also to execute on schedule and on budget. Once we get the approvals to do these projects, we need to do our job well and get the seismic mitigation work done. So with that, just a quick recap. Intersections, the little icon shows you there's Cajon Pass, and then there's that resiliency triangle pyramid. And again, it's not just linear, it's even more focused at the top. So even strengthens our resolve to really focus in on our most critical facilities as we work towards spending efficiently our ratepayers' dollars to achieve seismic resiliency throughout our system. With that, I'd like to wrap it up. Thank you.